Gaussian elimination is a powerful method for solving systems of linear equations. This process will help us simplify multiple equations and find solutions step by step. A system of equations is a collection of mathematical expressions that share unknown values. Our goal is to find the values that satisfy all equations at the same time. Instead of working with equations directly, we use a structured format called an augmented matrix. An augmented matrix is a way of organizing the equations by placing the numbers that represent each unknown in a grid. The left section contains the coefficients of the unknown values, and the right section represents the constants. This format makes calculations much easier. To solve the system, we transform the matrix into a structured form called row echelon. In this form, each leading value in a row appears to the right of the leading value in the row above. If there are rows that contain only zeros, they move to the bottom. The first non-zero value in each row is called a pivot. This arrangement makes solving for unknowns more straightforward. Gaussian elimination is achieved through three key row operations. The first is row swapping, which involves changing the order of rows to position them correctly for calculations. The second is row scaling, where a row is multiplied by a constant to adjust its values. The third is row replacement, which consists of adding or subtracting a multiple of one row from another to create necessary zero entries. These steps systematically organize the matrix to make solving for unknowns easier. Let's solve this equation step by step using the Gaussian elimination method. The first step is to rewrite the system in a structured format known as an augmented matrix. Since the leading value in the first row is already 1, no modifications are needed for the first column. As mentioned earlier, any number beneath the pivot should be 0. Looking at the first entry in the third row, it is currently 2. Because this value is positioned below a pivot, we must eliminate it. To achieve this, we subtract 2 times the first row from the third row. This operation successfully transforms the first entry in the third row into 0. Now, we adjust the second pivot by dividing the second row by 3, ensuring that all leading entries are set to 1. Next, we eliminate the entry in the second column of the third row. This is done by adding 5/3 of the second row to the third row. After completing this transformation, our matrix is now in row echelon form, making it ready for back substitution to solve for the unknowns. You could technically skip this step, but I have included it to enhance clarity. Here, we take the row echelon form of the matrix and rewrite it as a system of equations. This makes it easier to see the relationships between the variables before proceeding with back substitutions to find their values. Now that the equations are clearly written out, we start with the third row, which tells us that the value of the last variable is 3. Substituting this into the second row allows us to determine the value of the second variable, which simplifies to -2. Next, we take these known values and substitute them into the first equation. This allows us to solve for the final variable, which is determined to be 1. Thus, our final solution is as follows. The first variable is 1, the second variable is -2, and the third variable is 3. Breaking the process down in this way helps illustrate how Gaussian elimination transforms the system into a format that makes back substitution straightforward and easy to follow.